Welcome to our first module in our financial maths course, Discounted Cash Flows. In this session, we will be covering the following: the time value of money, how to calculate present values using the discounted cash flow methodology, also how to calculate the present value of an annuity, and to calculate the present value of constant and growing perpetuities. Let's start with the basic idea.
The concept of discounted cash flows relates to what somebody today would be willing to pay to receive a cash flow in the future. The underlying principle is that the sooner somebody is to receive a cash flow, and the more certain they are of receiving it, the more valuable it is today. We call money we receive in the future value, and its value today is called the present value. The concept of present value relates to the idea that money you have now is worth more today than an identical amount you would receive in the future. Why? There are three reasons. 1. Opportunity. We can invest the money today and receive more for it in the future. 2. Risk. There is no risk in having the money today, whereas if we wait until the future, there is a risk we may not receive it. And 3. Inflation. Because of inflation, money today buys more than an identical amount in the future. In order to determine the present value of a future cash flow, we need to discount future cash flows by a discount rate. This discount rate is often referred to as the required rate of return and is expressed as a percentage. The higher the discount rate, the more we discount the future value by, and the lower the present value. This is why the discount rate is also referred to as the required rate of return. The less we pay today to receive a cash flow in the future, the larger our return is. So here's a question for you. Which is more valuable to you, $100 today or $100 in 1 year's time? If you are like most financially rational investors, you would prefer to have $100 today. Remember our three reasons why $100 today is worth more than $100 in the future? This idea that money has different values to us today, depending on when we receive it, is called the time value of money. A simple example will help illustrate this further. Let's say you had $100 today and you invest it for 3 years in a bank, receiving an interest rate of 10% every year. Interest is paid to you at the end of each year and you choose to leave this interest in the bank. After 1 year, you would have $110. After 2 years, you would have $121, and after 3 years, you would have $133.10. Another way to think about this is, if interest rates were 10%, it would be financially equivalent to you if you received $100 today or $133.10 in 3 years' time. They both have the same value to you today. We can extend the previous simple example to derive a general formula linking the future value of a cash flow with its present value, where the interest rate is R. To increase the present value of $100 by 10%, we simply multiply the present value by 1 plus 10%, which we write as 1.10. We can do this for each of the 3 years, which is equivalent to multiplying $100 by 1.10 to the power of 3. This gives us a future value of $133.10 and provides us with an equation linking the present value with the future value. When we start with the present value and calculate the future value of a cash flow, as we've just shown, this is known as compounding. When we know the future value and want to work backwards to determine its present value, this is known as discounting, hence the term discounted cash flows. We can rearrange the previous equation so that we are calculating the present value rather than the future value. Rearranging this equation, we can isolate a term called the discount factor. It is this discount factor which we multiply the future cash flow by to determine its present value. Now let's look at a very common application of discounted cash flows called net present value or NPV analysis. Managers are often required to make decisions on whether a particular project is profitable. The typical project consists of an initial investment, in this case $1,000, and a stream of cash flows resulting from the investment. The cash flow at the end of year 1 is $400, at the end of year 2 is $600, and at the end of year 3 is $200. The net present value, or NPV methodology, sums the present value of the initial investment which is minus 1,000 as it is cash we are spending, and the present values of all the future cash flows. We can see the calculation of the year 2 discount factor, that is, 1 divided by 1 plus the discount rate of 10%, all to the power of 2. To get the NPV, we add all the present values together. If the NPV is positive, the project is profitable. If it is negative, the project is unprofitable. In this example, the NPV is positive, so this project is indeed profitable. We can use Excel to do our NPV analysis. Let's write our required rate of return in cell B1. Remember, this is R in the discount factor formula. The number we're using is 10%. Set up an Excel worksheet with 4 rows. These 4 rows will be time, future value, discount factor, and present value. Populate the time and future value rows using the information on the previous slide. Now we need to do the calculation for the discount factor. I'm going to link my formula with cell B1. We absolute reference this by pressing F4, then simply drag the formula across. The formula reads equals 1 divided by bracket 1 plus B1, which we absolute reference, close bracket, all to the power of time. Calculating each cash flow's present value is now simply a matter of multiplying the future value by the discount factor. And I can calculate the NPV for this project by summing together all the present values. We can see the present value at time 0 remains the same. This makes sense, as we are paying $1,000 today, therefore the present value of $1,000 today is $1,000. With the required rate of return of 10%, the NPV is positive, therefore based on this we would invest in the project. If the required rate of return rises to 11%, what is the new NPV of the project? Would you invest in this project or not? As you can see, when the required rate of return of the project rises to 11%, our NPV becomes negative, so we would not go ahead and invest in this project. Look at what has happened to each of the present values. They have become smaller. This is because we are discounting the future cash flows using a higher discount rate.
Now it's your turn to calculate the NPV. To go through our first exercise, click on the attachment link entitled NPV Exercise. Once you've had a go, compare your answers with the attached NPV solution. Good luck!
An annuity is a series of equal payments at equal time periods and guaranteed for a fixed number of years. Usually this fixed time period is 1 year, which is why it's called an annuity, but the time period can be shorter or even longer. Understanding annuities is crucial for understanding loans and investments that require or yield periodic payments. While we can calculate the present values of each future cash flow of an annuity to arrive at its present value, we can also calculate an annuity factor, which makes our task a lot easier. Let's look at an example. Say we had a 3-year annuity, receiving $100 starting 1 year from today for each of the next 3 years. How much would we be willing to pay today to receive this annuity if interest rates were 10%? Using our discount factor formula, where R is 10%, we can work out each of the 3 discount factors. Remember the formula is 1 divided by 1 plus R, all to the power of n. We can then easily calculate the present value of the annuity by first multiplying the future values by their discount factors, and then by adding all the present values together. So the present value of this annuity is $248.69, which is how much we would be prepared to pay to receive it. If you sum these discount factors, what do you notice? Our 3 discount factors we get when we calculate the previous annuity are 0.9091, 0.8264, and 0.7513 for years 1, 2, and 3 respectively. If we add the discount factors, we get what is known as the annuity factor, in this case 2.486. This is very useful, as it provides a shortcut to calculate the present value of an annuity. Notice if we multiply our annuity payment of $100 by the annuity factor, we get the same answer as before, $248.69. We can also use annuity tables to work out our annuity factor to save even more time. Annuity factor tables can easily be used to save us from having to add the individual discount factors to derive an annuity factor. Typically, as in the case of this table, the number of years the annuity lasts for, or N, is placed down the left-hand side of the table. Along the top row of the table are the various discount rates, or required rates of returns. As you can see from this annuity table, if we went down to the third row and across to the 10th column, the annuity factor is 2.4869. Let's now look at a practical application of annuities. Annuities are often sold as investments. Investors pay a lump sum today to receive a fixed amount at fixed time intervals in the future. You can find a PDF copy of the annuity tables under the Attachments tab. This particular annuity pays investors $15,000 every year for 10 years and offers a return of 7%. To find the present value or the price of this annuity, set up an Excel spreadsheet with the discount rate in cell B1. Set up 4 columns, time, future value, discount factor, and present value respectively. Time will go from 1 to 10. And the future value is $15,000 each of these 10 years. We need to insert the discount factor formula, which reads equals 1 divided by bracket 1 plus B1, close bracket, all to the power of A4. We can now fill this formula down. Finally, we can calculate our present value by multiplying the future value by the discount factors. Summing these gives us a present value or price of the annuity of $105,354. Adding the discount factors, we get an annuity factor of 7.0236, which when we multiply by our annual payment of $15,000 gives us the same price of $105,354.
Okay, now it's your turn to try this out yourself. Click on the attachment link entitled Annuity Exercise. Once you're finished, check your attempt with the attached annuity solution. Good luck!
A perpetuity is an investment that has no definite end, a stream of cash payments that continues forever. Mathematically, the sum of an infinite stream of numbers is undefined. However, the present value of a perpetuity is not undefined, as eventually the future cash flows are received so far into the future they have no value to us today. A real-life example of a perpetuity are war loans, bonds issued by the UK government with no redemption date. Also, income from real estate can be considered a perpetuity if we assume we will receive rent from it into the foreseeable future. We will look at 2 types of perpetuities, constant and growing perpetuities. Let's say we deposit $100 today. If interest rates are 10%, in 1 year's time I would have $110. I could withdraw $10, leaving $100. I leave this $100 in the bank for another year, and at the end of year 2, I would again have $110. I could withdraw $10, leaving $100, and so on. In other words, I have created a stream of $10 every year forever, starting with $100. Therefore, the present value of a perpetuity, if interest rates were 10%, paying $10 every year is $100, which we can also write as $10 divided by 10%. So, from our example, we can see that it is possible to calculate the present value of a cash flow which will occur in perpetuity. The present value of a constant perpetuity is the payment we are to receive into perpetuity divided by the discount rate or the required rate of return. Using the figures from our previous example, you can see that this formula gives us the same present value of 100. A growing perpetuity is again a stream of cash flows that start 1 year from today and go on forever. However, the amount that we receive grows by a constant growth rate g. We can calculate the present value of a growing perpetuity by using the following formula. The present value is the first payment we received 1 year from today divided by the discount rate minus the constant growth rate. As a demonstration on the use of a growing perpetuity, put yourself in the position of an analyst trying to value a dividend-paying stock. Let's assume that the price of the stock is equal to the present value of all the future dividends you will receive from owning the stock. This is a fair assumption to make if you intend to buy and hold the stock for a long period of time. Let's now assume that the dividend you will receive 1 year from today is $5, but the company's dividend policy leads you to believe this will grow at a steady rate of 1% per year. Let's insert these two variables in cells B1 and B2. Finally, let's say your required rate of return is 10%. Let's insert this value into cell B3. In cell B5, I'm going to type my growing perpetuity formula, which will read equals 5 divided by bracket B3 minus B2 close bracket. This gives us a present value of $55.56. If the stock is trading below this figure, this may represent a buying opportunity for us.
For our final exercise, we'll look back at everything that we've discussed in this module. Click on the attachment link entitled Prize Draw Exercise. Once you've had a go, take a look at the attached prize draw solution to see if you get the same answer as me. Good luck! That concludes our first module in this financial math series on discounted cash flows. There are some key messages for you to take away from this module. The time value of money states money received today is worth more than an equivalent amount received in the future. The discounted cash flow methodology uses a discount factor to find the present value of a future cash flow. Single cash flows, annuities and perpetuities are all types of investments we can calculate the present value of using the DCF framework. In Module 2, we extend our discussion on discounted cash flows by applying some of the same techniques to price bonds. I hope you can join me again. Goodbye.